Hello all, welcome back to yet another problem of Lead Code's daily challenge. The problem is all paths from source to target, and given a directed acyclic graph DAG of n nodes labeled from 0 to n minus 1, find all possible paths from node 0 to node n minus 1 and return them in any order. So the graph is given as follows. The graph of I is a list of all nodes you can visit from node I, that is there is a directed edge from node I to node graph of ig. So what does that mean is, so this is the graph. So the zeroth node is connected to 1 and 2, that is nothing but you can see there is a connection, there is a path between from 0 to 1 and 0 to 2, and the first node is connected to node 3. As you can see, there is a path between 1 to 3, and the second node is there is a connection from, there is a directed connection to node 3. So you can see there is a directed connection between 2 to 3, and for the third node, which is the last n minus 1 node, it is an empty vector because there is no path, there is no out degree that is going from n minus 1. So we want to find all possible paths. So for this example, there are two paths that is existing from 0 to n minus 1, which is nothing but 0 1 3, and the other path is 0 2 3. So this is what the problem requires. We want to find all possible paths from node 0 to node n minus 1. So what we can do in example 2, you can see the node 0 and the n minus 1 is nothing but there are 5 nodes, so n minus 1 will be 4. So we want to find all possible paths from node 0 to node 4. So for this, the output is nothing but 0 4, there is one path, 0 3 4, there is another path, and 0 1 3 4, there is another path, and 0 1 4, there is another path, and the other path is the 0 1 2 3 4. So there are almost 5 paths that are existing in this particular graph from node 0 to node n minus 1, which is 4. So we want to find out all possible paths. So the common intuition that comes to our mind, since it is a graph, this we can make use of DFS traversal technique, where we can explore all possible paths. And here what we can do is, we want to keep track of the nodes that we are visiting in that particular path. So to keep track of the nodes that we are visiting in that particular path, we can make use of some data structure, say a vector of in, where we can push the nodes into my vector, and we can do the DFS traversal from that particular point. And when we come back, we can just pop that node out, and we can select the different path, and we can obviously select the some other path, and we can explore all possible paths. And finally, when we reach the node n minus 1, we can push that particular path into my resultant vector of vector n. So that is how we can solve this problem, and we can use a DFS plus backtracking solution for this particular problem. And as you can see, the n is ranging from 2 to 15, and we are exploring all possible paths, and there will be many paths if there are many possible nodes that are connected to different nodes where it leads to node n minus 1. Then we will be tending to take, for each and every node, we will be tending to take some options like n options. So the time complexity for the solution will be 2 power n, and there will maybe another n nodes, n adjacent nodes. So we can generalize and say there will be 2 power n into n time complexity, and the space complexity will be an order of n, since we are using a graph, right, of order of n. So we and even we can make use of that auxiliary stack space is used when we are doing a DFS, and we are also having a vector, we are also having a vector in data structure, so we can say it as order of n. So the time complexity will be order of n, there will be n nodes, and the time complexity will be an order of 2 power n into n, since we can explore all possible paths. And the space complexity will be order of n, here there are n nodes. So this is how we can solve this problem. Now let us try to quickly code this approach. So what we need is we need a resultant vector, which is nothing but vector of vector int resultant, and I'm not going to create any graph using this connections, because we can use this graph itself to traverse in DFS, because zeroth node there are these are the connections, and for first node these are the connections, and the second node these are the connections, these are the nodes that are connected with. So we have the information in this graph itself. So we don't want to create another graph by using their information. So we are having a vector of vector int result. Then we are going to have a vector int data structure. And as you can observe here, we need to find all possible paths from node 0 to node n minus 1, and for that the first node is always the node 0 and the last node is always the node n minus 1. As you can observe, all the paths is having the same thing, and even in this example 1, the node 0 and node n minus 1 is the first and the last node respectively. So when we create this data structure itself, what we can do is we can push the node 0 into my data structure initially itself. Then we are going to do a DFS traversal where we are passing the graph, then resultant vector, then a data structure, and also we can pass the node 0. From node 0 only we want to start the DFS, and at the end of the day what we are going to return, we are going to return the resultant vector. Superb. Then our ultimate goal is to finish the DFS traversal. So this is going to be a void DFS vector of vector int graph, and then a vector of vector int resultant. Oh, great. Vector of vector int result. Then a vector int data structure. And another thing what we are carrying is int node, and we can also we can also keep track of n, because that is the node we want to reach, that is the target node we want to reach. So what we can say is we can pass n is nothing but the graph dot size. N is the graph dot size. So what will be our base condition? The base condition is very simple. What is that? If my node is reached, if my node is equal to n minus 1, we are also actually carrying the n, right? So if my node is equal to n minus 1, then we have reached the last node which is required in that path. So what we can do is we can push that data structure into my resultant vector, then we can just return. So this is going to be my base condition. Else we want to explore all its adjacent. So auto adjacent of my graph of node, what we want to do is we are going to explore the path. So we want to push the particular node into my data structure. Then we want to do a DFS traversal graph resultant data structure. Node is nothing but the adjacent node and the n is passed. When we come back, when we backtrack the data structure, we want to pop it out to explore the next new path. So yeah, just we can do a pop back. That's it. It is very pretty simple. The time complexity for the solution will be 2 power n into n, and the space complexity will be an order of n. Now let us try to run our code and let's see how it gets. Yeah, it gets accepted for the both example test cases, and let us submit the code as well. Great, it gets accepted. So hope you like the solution, and today is the 365th day of my daily challenge problems, and it is almost a year. I took the resolution a year back to do daily challenge problems daily, but I have I'm continue solving through YouTube recently only. So hope you like the solution. Let me know in the comments if there are any suggestions. Let us solve tomorrow's LeetCode daily challenge, and let us meet tomorrow. Until then, bye.